Definition of disjunction. If P and Q are statement variables, the disjunction of P and Q is P or Q, denoted as P or Q. It is true when either P is true or Q is true, or both P and Q are true. It is false only when both P and Q are false. And so this is the formal definition for disjunction. And what do we know about disjunction? It's this symbol, and it means or, and we remember it like this, or, and denote it for or. So that's everything. If P and Q are statement variables, the disjunction of P and Q is P or Q. So we know that. Denoted P or Q, which we know. And so this is the new stuff we're going to go over. It is true when P is true or Q is true, or both P and Q are true. It is false only when both P and Q are false. So now we're going to make a truth table. And we got two statement variables. So if this, so we know what P and Q are. And what are we trying to prove? We're trying to prove P or Q, the disjunction. And so we're going to do what we did, true, true, false, false. This is true, false, true, false. P or Q. So if it's one is true, then it has to be true. If they're both true, it's true. So one is true, the other one's true, then it has to be true. If they're both false, then they're both false. And so thus we proved the disjunction. So thus we prove disjunction. Definition of statement form. A statement form, or propositional form, is an expression made up of statements variables such as P and Q and R, and logical connectives, such as negation, and or. Right here, or. That becomes a statement when actual statements are substituted for the component statement variables. A truth table for a given statement from form displays the truth values that correspond to all possible combinations of truth values for its component statement variables. And so this is just a more formal definition of statement. And it explains what the symbols are called. They're called connectives because they connect statements together to make compound statements or certain different new phrases, right? And so that's just another word we could use. Connectives. So some word you could put in your vocabulary. And that's about it. It just says that we also like to use truth tables such as P and when we have the P and Q and so forth. And so that's just a new definition. I'm going to make a truth table for the exclusive OR. And so if you remember the last video, we were explaining the exclusive OR, and we showed you the expression we use. Well, this time we're going to actually prove it. And so let's show what that looks like. We're going to have a statement that looks something like this. It's going to say P or Q. It's going to be in the parentheses. And so something to note when you're proving these, you always do what's in the parentheses first, and then outside the parentheses, and then outside the parentheses until you get outside, right? So remember when we learned about do the parentheses first, then the negation, and then the conjunction. So we're gonna learn that right now. So anyways, right here, there's another way to write this, and so I'm gonna write it over here so you can see it. It's gonna be abbreviated, so we don't have to write all this, but right now we write all that so you understand it. So this is when you get comfortable. This is the more simple version. All this means is exclusive or we could write it like this. And I haven't seen anyone write it like this before. Rarely. We mostly would use this one. And then you guys are still learning this, so we're focusing on proving this statement right now. And that's all that means. So let's go prove it. So we gotta make a truth table. So how are we gonna do that? Well, we need to set up columns for P and Q. And what's our P and Q again? That's our components slash statement variables. And so there's a lot of different words we use for logic, so they all go hand in hand. And so we remember what we do. It's 1/2 n. Or actually 2n, right? This should be 2n first, and this is 1/2 n, just in case you forget. And so this is going to be true, true, false, false. Remember that it's a pattern. And if you don't remember that, I highly suggest you watch the other videos. And then this one's going to be true, false, true, false. And you could clearly see that you could easily mess up. You're not careful. And so now we need columns separate for each of these phrases, compound statements. So now these are our statements slash variables slash components, but now we want to make compound statements. And so my first one's going to be P or Q. And then our next one's going to be P and Q, right? Because that's two compound statements that it's said in our sentence. Alright, this is our sentence. Just symbolic. This is our variables, so I'll just put V, VAR. And these are our compound statements slash statements. These are statements too. So now that we're back on this, let's get this done. And so then we're gonna have another compound statement that's gonna be the negation. And then finally, at the end of this, we're gonna have our sentence. And what does our sentence say? Our sentence says P or Q and the negation of P and Q. So that's pretty simple. Alright, so what's the first thing we need to do? Remember we prove or and we prove and. So what the definition of or says, if either P or Q are true, then one of them is true. So that's true, that's true. And then the last thing I said, if P and Q are false, then the whole entire statement's false. And so right here you clearly see that it's both false. And now we're going to have our next statement that says P and Q. And that's only true if the whole entire statement is true. And the rest of these are false. And then we have the negation, P and Q. And so, how do you do this one? Well, we just simply look at our P and Q, and it's going to be the opposite of our P and Q. So if this is true, then this one's going to be false. If the next one's false, 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 then all three of them have to be true. So there we go. We did our variables and we did our compound statements. Now we just need to figure out if this is true for the sentence. And so how do we do that? Well, we gotta look at our table right here. And so what are we gonna look at? So I'm gonna use a different color, then we'll use this green. We're gonna look at this, and for whatever is true, so these are true, and that's what we're looking at. So we already know this one's not gonna work. We already know this one's false because I'm gonna use pink for it because of that, right? So we already know that one's false. Alright, so what's the next thing that we need to look at? Oh, we need to look at right here. This statement. And what's true? These are true. But this is false. And so we already know this is going to be false. Because that portion of the sentence is false. Or this statement is false. As you can clearly see here. Right? This I'm going to draw right here. I'm going to probably use a different color. This statement right here is false for that part. Just to clarify. And now we got two more just to look at. Right, we just have to figure out these next two right here. And so, what are we looking at? We're going to look at this. So I'm going to circle it green. And we're looking at this. And so it looks true. And when you get better at these, you just see it right away. And now we look at this. And we look at that. And so that is true. And so this table we didn't really need. But if you're still trying to get the hang of it, then you probably want to write it out. Because then you know that this is a negation. So we didn't really use this table to figure out our sentence. But it helped us to figure out our statement. And so what did we figure out? We figured out that there's only two ways that this sentence can be true. This next question is asking us, construct a truth table for the statement form P and Q or the negation R. And so feel free to pause the video and try it yourself. Because this one's going to be a little harder. Let's do it. So we have three statements slash variables. And what are those? It's going to be P, Q, and R. So we identified what our variables are. So we're going to have once you put your variables down, you just put a line down. And you continue this line. And so what's a part of our statement? We're going to have P and Q. That's one part of the statement. And then what's our next part of the statement? It says and, or so actually it says or, negation or. And so we're going to have something that's going to say negation or. It's going to have this symbol R. It is not R. And then you're finally going to have your whole entire sentence written out. And so the whole point of doing these problems is to be able to tell how can this be logical, right? And what do I mean by that? I mean, there's only a couple scenarios in which your sentence could make sense. And so that's what we were trying to figure out. If there's only a couple ways your sentence can make sense, then you can't say something that doesn't make sense. And these are just a theoretical way of showing it. Alright, so right here, what's the first thing we're going to do? Remember what we said? We got to do 2n. That's the first thing we do. And it goes straight down. And so we had three variables, so 2n makes 8. And so I'm not going to write it out. we're just going to let you do it. So then we're going to put true, true. And then what's our next step, if you remember? It's going to be 1/2 n. And how many variables we have? We have 3, that'll be 8. And so this one's 1/2, this is 1/4, and this is 1/8. So true, 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 false, 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 false. And so the next one, you remember what I said, it's 1/4. So every 1/4 of this, which is going to be 8 out of 8, right? It's going to be true, true. And then the next 1/4, false, false. And then the next 1/4, so that makes 3/4. True, true. Until we get a whole right here, so it's going to be false, false. And how do you remember if we did it right? They're all going to say false on the bottom. They're all going to say true on the bottom. That doesn't necessarily mean you did it right. It just means that you have a higher chance that you did it right. And so the next one, it says true, false. And so the best way to check is just to go through the process again. So true, false, true, false, true, false, true. And so now you get all the outcomes for your permutation. And we're going to learn about that later on in this class. So right here, we have P and Q. So we're only looking at these two. When is it true, when is it false? So false, 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 true, true, false, true, false. It's only true for 2 times. So it's going to be true, true, and the rest is going to be false. And I'll put it this color. And if you can see right here, false, true, false, true, false. And if you remember what our n, it has to be true for both. So these past videos, there's been a lot of these on this chapter because this chapter takes a little long, and the following chapters take a little longer. So we got negation or it says true, false, and it's just going to be the opposite of that. And so this is going to be opposite, right? So let's see. It's going to be false, false. So for every true, there's a false. And for every false, it's going to be true. And like I was trying to tell you right now, it's going to be long because doing stuff like this takes forever. And you'll learn later on why it's so helpful, because it just helps you to understand statements and logic better. So P and Q, or negation or. So now we got to look at these two statements and see where is it true. And so I color coded it so we could just be able to tell right away. So right here is true. And actually it says P and Q or R. So if one of them is true, then the statement is true. Right here the statement is true. Right here the statement is true. And then right here the statement is true. And so we're going to have something that looks like this. So I'm going to just use the green color. So let's say true, true, false, right? Because this is both false. For or statement, you need one of them to be true. You can have all of them. You get what I'm trying to say. You remember the definition. So we count, we have 1, 2, 3, 4, 5. 5 out of 8 different outcomes that this sentence could make sense. And so that's just the gist of it. And so let me find anything to say about this. So the whole point of doing this is to learn logic to help judge the truth of a compound statement. Logic can't help you to determine if a statement is true or false. Rather, it allows us to understand the information as a whole. And so I've been trying to say that. So I just said it again right now, so just to know that this is not going to be like true no matter what, right? You gotta use a lot of different factors. And it's not a philosophy class, so we're just learning this so we learn the basics. Alright, so let's go on to our next thing. Logical equivalence. And so, just before we start this, I want to show you what logical equivalence looks symbolically. So, it's going to look like an equal sign, but with 3 little signs. That means logical equivalence. And so we have this statement right here. And this statement says 6 is greater than 2 and 2 is less than 6. And so let's write it out so we could see it more visually or symbolically. So 6 greater than 2. And we have, right, this symbol here, and 2 is less than 6. And so what do we know about these statements? They mean the same thing. And so what do we say about these statements? We say that they're logically equivalent. So we use this symbol. So then let's say we wrote this symbol out. And so I'm just going to not take that much time. So when we say these two statements, then we put this sign. It's like an equal sign, right? But we say they're logically equivalent. And that's mostly used when you're trying to argue a point or prove something. And so now we're going to have more of a real world example. And we're going to use this. We're going to say dogs bark and cats meow. And so what do you think about this? It sounds like a funny, well, compound statement, right? Because we have a P right here, dog barks, and a Q, cat meows. And so now we're going to have another statement. This statement's going to say cats meow and dogs bark. So what do you think about this statement? It looks like it means the same thing as number 1. And so what do we say about that? We say that this statement is statement 1 and statement 2 are logically equivalent to each other. And I want you to get used to writing that out. Right? If you're given a problem like this on your test, you're going to have to write it out as a sentence. So how are we going to say this? We say, well, we could say statement, or let's use an actual sentence. Our statement 1 and 2. And you could, if depending on they're telling you to identify what kind of statement, then you say compound statement. So our compound. So just so you guys understand what's happening, you know that these are compound statement. Our compound statement 1 and 2 are, and then you could say logically equivalent. And if they want you to write it, and I'll write it another way now, logically, let's see, equivalent. And so if I spell something wrong, it's okay. It's just know that I mean I spelled it right. So equivalent. So hopefully I spelled everything right. So now I'm going to write it out symbolically. And so we're just going to say right here. Let me see if I can get it right. There you go. So let's say dogs bark, it's going to be P. So let's go back. Right here we're going to say dogs bark is P. Let's denote that it's P, right? And then let's say cats meow is Q. We're going to use orange. So then what do we do? We know that this is an N and this is an N. So we're going to put P and Q. And what's the three signs you're going to put? That's like this right here, right? Means it's logically equivalent to Q and P. And so if you had a test, right, you want to put it either depending on what they say. It might say, ask you, depending on how your professor phrases his example for the test, you might want to put this is your common form, and symbolic form, and component form. And you could just tell him, he'll understand what you're saying, he or she. And then you say this part, it's more of a informal. In mathematical sense, right? That's an informal. So we say informal, or we could say English, or we could say, I'm just giving examples of what they might say on the test. I can't really think of anything else. So sometimes we say written out as words is informal, or they say write it out in sentence format. And so I'm just giving you ideas. It just depends how your instructor phrases his train of thought. So that's just some ideas of how they would write it out. So now we're going to look at proving this. We're going to prove this statement. Ready? So what is the first step we do? And so I'm not going to write out those well, I just did already. I'm not going to do this anymore. So if you get it, you get it. If you don't, I highly suggest you keep doing it. So if you want to pause the video anytime, try it. Because I don't want to take more of your time. So now we're going to do it a little faster. So it's going to say true, true, false, false, true, false, true, false. And why is that? Because remember the other rule that I said? The other, you know what I'm trying to say. We only go half of what our first statement says. And so now we're going to have P and Q. So we have P and Q. And so that's going to be true, right? The rest are going to be false. And so when you work with these, you notice that there's always some kind of pattern. So let's say I have a P and Q. I know that always the first statement is going to be true, the rest are going to be false. And that's only if and only if you write it the way I taught you how to write it. If you write it any other way, you're not going to get this kind of statement. Right? Because I told you you could write it any way you want to, but I told you this is the most efficient way. And so now we're going to have this, and it's going to say the same thing. It's going to say true, then the rest are going to be false. And why is that? Because we need to have both of them to be true, right? We need these two true. That the rest right here are false. You can see right here, false, 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 false. Therefore, the rest are going to be false right here. And so, what do we call this? When we have both these statements have the same truth value. Well, we say that they are logically equivalent. And so we just proved that P and Q is logically equivalent, which is this sign right here, right? To Q and P. And so what is this rule? We've been talking about it for a while. So thus we proved, and then alright, type it. We're just going to type that out really quick. Proved. And so we learned about this, we call it something property. So what property is it? You prove P, so when you prove this, you gotta put something like this, which just means thus. We prove this kind of statement, which is logically equivalent to Q and P. So there we got our answer. But now I'm posing another question to you, and that question is, this is called, and we call it the commutative property for algebra, but in this case we call it the commutative law. And so I'll just type it for you because typing is a little faster. And so that's our commutative laws. And so I'm going to make a video proving all the logical equivalent laws. But this is just one of the many laws. And so I highly suggest to you prove this yourself, and you prove it backwards. So it's going to give you the same thing, right? So you just got to switch these. And you'll be the same thing, but on the test, they'll want you to prove it the other way. So keep that in mind. So we're going to move on to the next question. So we just shown an example of logical equivalence. So now we're going to explain the definition. So two statements forms are called logically equivalent if and only if they have identical truth values. And we just saw that by the truth tables, right? And we remember how the truth tables look. For each possible substitution of statements for their statement variables. And so we remember our statement variables are these. And substitution of statements just means that they make sense in terms of what question we're posing. So let's say we're posing this question. The logical equivalence of statements forms P and Q is denoted by writing P is logically equivalent to Q. And so it's just saying that this is how we write it out. And so we don't have to worry about that. So that's why I didn't write out the definition here, because it's not as important. We're experiencing it hands-on. And so two statements are called logically equivalent if and only if they have logically equivalent forms when identical component statements variables are used to replace identical component statements. And so that was just the same definition, except explained in a different sense. And so that's all we really need to know about that. And the last thing I need to tell you is the two different ways we could check if something is logically equivalent. And so the first way, so this is a little more important, is to construct a truth table. Just like we just did right now, right? We constructed a truth table, and then we clearly saw that it was logically equivalent. And then the second thing is to check each combination of truth values of the statement variables. And so what that really means is when we're given a statement, and we'll see right now when I'm just gonna put when we have a statement written, I'm gonna put it at the end written. We are gonna be able to tell just by looking at it. So we're gonna say statement / sentence over here. So don't get caught up right now on this, because we're gonna look at an example right now, and then from that example we're gonna look at this idea again. So two ways to see if something is logically equivalent. Construct a truth table, which should say truth in here. Sorry about that. and say truth table, error examine or statement slash sentence. And that's more of a regular way we do it, right? If you're given something like to prove that something is wrong, we're not going to construct a truth table to be able to tell if that statement is logically equivalent to this other statement. We're going to examine the definition, the statements that are said. And so we're going to take a look right now at an example. Thank you for watching the video. If you enjoyed the video, please give it a thumbs up and subscribe to the channel. It will help a lot to allow my channel to keep growing. And if you have any comments, please leave it down below in the description. And if you have any ideas for the future or future content you want to see, please let me know too. And I hope I can see you guys next time. Thank you, everybody, and goodbye.